Hello. Welcome to the final week of presentations for Philosophy of Science. I'm Travis Draper, and I will be talking about whether math exists and whether or not it ought to be used in science. For full disclosure, I am quite biased toward believing that math does exist, and I both expect and hope that you will form your own opinion on the matter. The interaction in the comments on the discussion page in Canvas should prove to be very interesting. To start out, let's talk about the basic foundations of mathematics. The basic foundation of any mathematical theory and any mathematical thinking are things called axioms. Axioms are assumptions that are determined to be true or believed to be true, which cannot be proven true based on any other true or false based on any other prior assumptions. An example of this would be the existence of the number 1 or the existence of a 0. Like, you cannot prove the existence of 1 and you can't prove the existence of 0 based on mathematical logic, but based on those and a few more axioms you can start to build up a crude system of devising arithmetic. And the most important function of axioms is describing arithmetic. An early attempt at an axiomatic system was presented in probably the most important mathematics textbook in all of history, is The Elements from Euclid. In his introduction to his book, which was a series of problems for students, one of the things that they were asked to that students were told to assume is that no two parallel lines ever meet. And it was problematic because a lot of people thought that that might not be axiomatically true and it might be provable via some other means. And through many centuries of work, it turned out that Euclid's parallel postulate turned out to be a false statement. While in Euclidean space, or flat space, given a line and another point separated from that line, there is exactly one line that does not intersect with that initial line. But there are other cases, such as in hyperbolic space or in elliptic space, that you do not get the same relationship. And so one of the things that we note from this is that while Euclid was focused on geometry in flat spaces, mathematics is capable of talking about things that don't even properly exist in the real world, such as hyperbolic geometry, and which cannot be embedded properly into our standard Euclidean space, which is basically you cannot embed certain things into our current geometry of our universe. Now, given a set of axioms, axioms are typically fairly boring. If you were to try and do mathematics based solely on a set of axioms which you were given, you would probably find that you can't do very much. One thing that mathematicians like to do, and it's typically their job to do, is take things that the axioms describe and create and define new objects that are based on those axioms. Initially, in most axiomatic systems, you get the natural numbers 0, 1, 2, 3, 4, 5, etc. But it becomes useful to define ratios and fractions, but those aren't built into axioms, and so then you define new operations in mathematics. And as you keep defining new relations, you can create objects such as prime numbers, which the prime numbers exist, they are just a defined class of numbers. And One of the projects for mathematicians initially was to try and create a perfect axiomatic system, a system of axioms that could prove all of mathematics and would not generate any contradictions. There have been many famous attempts at this, although eventually a mathematician named Kurt Gödel proved a theorem called the Gödel incompleteness theorem, and it's known by a few other names, which basically states that you cannot have a both perfect and complete mathematical system, meaning that any set of axioms that can describe arithmetic or basic arithmetic functions, you then are unable to prove true statements. There are going to be statements which are true, but which cannot be proven. And in other cases, any system that tries to be able to prove all true statements to be true would then generate inconsistencies or paradoxes. One such attempt at a very good system of axioms, wound up generating a paradox, which a lot of people have heard of, which is the set of all sets which do not contain themselves. That set of axioms has since been abandoned, but it influenced the creation of a new set, which is the foundation of most of modern mathematics, which is known as the Zermelo-Fraenkel set theory, which to this point has not generated any paradoxes, but it is also known that there are many true statements, or there are many statements that cannot be proven. There are several statements which have been proven to be unprovable within the assumptions of Zermelo-Fraenkel set theory. The concept which is held to be the most common realist view of mathematics is known as Platonism, which is essentially the view that mathematical objects are real, but they don't have a physical or spatial existence. They're abstract concepts that are unchanging and have static properties over time. And the relations between these objects are what is studied in mathematics. This is sort of similar to what is likely to be your view of numbers. They're just things, they're abstract ideas, abstract concepts. One of the things you can think about is the relations between mathematical concepts, which is what is mainly studied in mathematics, are similar to the relations between different biological systems or physical systems. Relationships exist, like, for instance, the relationship between you and your parents exists, but it doesn't have a physical location. Like, where is your friendship? Like, it doesn't have a physical location, but it is a real concept, or at least I hold it to be real. It could be argued that it is a fiction, which does bring up one of the main anti-realist views of mathematics, which is known as fictionalism, which basically holds that mathematical concepts, such as the ones studied in A History of Mathematics or discussed in A History of Mathematics, are no more real than the characters in any fantasy book or any novel. So while, like, mathematics can convey truth, it is not in itself the location where truth is. One objection to this is that in opposition to, like, fictional characters, like, mathematical objects have a consistency. When you're trying to prove something, there are things that, when you're working on math, there are things that are objectively wrong. You can make wrong choices in a proof. There are ways that proofs must go in order to remain correct, whereas in any fiction that we know of, it doesn't choices don't necessarily matter. Exist poor literary choices, but those aren't actually uh, like falsehoods. One thing to look at in relation to, insofar as the relationship between mathematical realism and physical realism for science is that, for, exa- for example, the interpretation of what an electron is has changed many, many times over the years. First, it was viewed to be just a solid sphere of charge, and the interpretation of an electron has changed over the years, and it perhaps might change again. Whereas the oldest mathematical proofs are still considered valid, at least under the system of axioms that were used to prove them. So essentially, since mathematics has a long-term consistency, one might be inclined to view it as perhaps more likely to be real than any interpretations of physical theory. And if mathematics doesn't happen to be real, well, mathematics kind of it gets fuzzy, but mathematics is the field under which logic lies. Technically, logic lies the boundary between mathematics and philosophy. And if mathematics isn't real, then that would imply that much of logic, and therefore like the logical discovery of things, would also not necessarily be real. The consequences of this would make much of science rather difficult to continue, given that if any science is to be true, or any much of science relies on mathematics, and so if we need science to contain truth and convey truth, which is part of what we have defined as the search for science. It's a search for things that describe in a consistent way how the world works through the scientific method. If that is to work through like the logical deduction, then we need at least some form of logic to be real or true. If we are willing to accept that math is true, or at the very least is capable of describing truth and the relationships between different concepts, then we can contend with a more interesting question about whether or not math is as effective as it reasonably needs to be. Um, According to Eugene Wigner, math is unreasonably effective at describing things in science. While although that opinion is shared by some people, it's not necessarily the opinion of everyone, because there are branches of science that have a harder time reconciling their discoveries with already described mathematical principles. But in the early days of physics, at the very least, calculus was designed essentially to aid in the calculations that were being done at the time. And it turned out that calculus had a lot of predictive power when it came to describing the motions of physical objects. And outside of physics, there are also mathematical concepts that seem to be rather good at describing natural phenomena. For instance, in biology, to describe population levels, logistic curve is often used to try and describe how a population changes over time as it grows and reaches and approaches the carrying capacity of an environment. Now, these population graphs are very useful, but it turns out that most of these population graphs are they're continuous. They deal with um, discrete values in their it has a range of discrete value of continuous values. So, but in real life, you can't have square root of two birds in in a population or living in an area. So the math is the nice math often tends to be a bit easier to deal with, but doesn't describe perfectly the situations we're dealing with. Mathematics is often based around approximations, especially when we get to systems where we can't measure things perfectly. Like in biology, you can't always measure every aspect of a biological system perfectly. And so you need to deal with approximations and a little bit of corner cutting in order to have a mathematical model that you can at least make sense of, or that you can reason with and modify in a reasonable amount of time. The complexities inherent in natural systems mean that doing math to calculate the basic laws or patterns found in the data we gather from observing natural systems becomes really, really hard to do. One instance of a natural system that has high amounts of complexity arising with seemingly low, which should seemingly be easy, is something known as the three-body problem in physics, where you have three roughly equal masses orbiting in a gravitational system. It turns out that these orbits aren't particularly stable and they describe a chaotic motion. And similar things occur with double pendulums, which, while they should seem to be easy, single pendulum is relatively easy to describe. It's something that you learn in first year physics, often in high school or your first year of college. But once you add in a second pendulum dependent on the position of the first, you wind up with a system that just doesn't always do the same thing, and you can't predict what it's going to be like very far into the future. And these chaotic tendencies in physical systems really tend to make the math quite difficult to do. But just because the math is hard doesn't mean that it's not useful. Um, and so, because math is a tool, much like tool for discovering and describing things, it means that we can, although the math to describe these chaotic systems is hard, the math can still at least be done. Like, for example, meteorology is still done, and it's still reasonably accurate, even though it's dependent on a system with potentially millions of variables that vary chaotically. Um, Another reason that math is important for science is that it's not necessarily restricted to a single domain or a single viewpoint way of viewing the world. Um, for instance, math can describe things that have a higher dimensional systems, like four-dimensional cubes and other objects that might arise in data in when arise when collecting data, but don't necessarily exist in the real world. So the capability of math to be robust to describe things that can't even exist in the real world makes it a useful tool. And so just because it's hard to do doesn't mean that it's not useful. And another instance where math can describe something that seems like it wouldn't exist in the real world, like objects that don't have an integer dimension number, like one-dimensional line or two-dimensional flat plane or three-dimensional objects. There was the discovery of fractal objects, which is the existence of something that has dimension of 1.5, or has a dimension that isn't quite has properties that aren't described, that don't quite fit in a set of dimensions. And it turns out that this branch of mathematics is actually quite useful in describing coastline variation and in describing uh, how tree roots branch and other objects like this. And being able, and the ability for math to be able to generalize to types of systems that we wouldn't necessarily think exist in the real world means that it has quite a lot of ability to describe stuff. And although it can't describe everything perfectly, it can describe a lot of things quite reasonably well if we take the time and effort to analyze data and generate potentially new types of math to describe what we're observing in the real world. Okay, so what have we learned from this? Essentially, we've learned that because mathematics is so robust and it has an ability to be adapted to describe both physical phenomena and things that can't even exist in the real world while still maintaining logical consistency, this foundation, and it basically forms the foundation for all of modern science. And although the questions as to whether or not math is real or whether we can believe that the things that mathematics tells us might be tedious or seem kind of like a nuisance, it's important to always be questioning our fundamental assumptions about the world, the things that we assume to be true but we cannot necessarily prove. Always questioning those and trying to determine whether or not we can believe those things, even independent of a proof that can be made for them. Uh, Thank you all for watching my presentation. I've left some links to YouTube videos that cover these topics in a much more entertaining fashion in the description on this YouTube video, if you feel inclined to take a gander at them. Have a good one, and DFTBA.